Hi, everyone. My name is Emmanuel Thompson, and I'm a professor of actuarial science and statistics in the Department of Mathematics at Southeast Missouri State University.
My name is Mohamed Abu Sheha. I am assistant professor in the Department of Mathematics at the Southeast Missouri State University.
We want to thank you all for coming, and today our presentation is going to be on the topic, a hybrid decision tree KNN framework for classification with nonlinear effects and local variation, a Bootstrap simulation study. So by way of outline, we start with an introduction, then the methods, we give you the results, conclusions, and then references. So in terms of background, I'll say decision trees and KNN are both supervised machine learning methods. And I also want to add that while decision trees are widely used for their interpretability and flexibility, their predictive performance may decrease when the underlying class structure exhibits substantial local variation. And here, when I talk about local variation, all that I'm trying to say is that with regards to decision trees, once there is a small change in the data set, it leads to dramatic change in prediction. Also, decision trees are prone to overfitting when dealing with complex data sets, which means that if you use the decision tree, in terms of the training set, they perform extremely well. But then if you deploy them on the testing set, it performs woefully. Then we say that the method is overfitting. Okay. And also, the performance of KNN degrades significantly with high dimensional data. So selecting an appropriate value for K is critical. And here K is actually the number of nearest neighbors of a test point when we want to make prediction in KNN. So in terms of purpose of the study, so we'll say is to develop and compare the predictive performance of decision trees in a hybrid method. And that hybrid method combines decision trees and KNN within the steps of bootstrapping. And in terms of objectives, we have three of them. So the first one is to evaluate the predictive performance of the decision tree by varying the number of observations in the terminal node, and we use bootstrapping. Then in the second objective is to evaluate also the predictive performance of the hybrid method. But this time around, we vary the number of observations in the terminal node for the decision tree. However, for the KNN, we vary the number of the nearest neighbors, still within the steps of bootstrapping. Then in the third objective, we compare the first two. Now, let's look at the methods. So a hybrid classification approach, like I said before, combines a decision tree and KNN. With regards to the decision tree, is for what? Global partitioning. However, for the KNN, we use that for local refinement. They'll become more clearer when we reach the results section. And then bootstrapping actually is applied to estimate the average misclassification rate. And then a bootstrap quantile interval is created. So here the bootstrap quantile interval is used to kind of estimate the precision or the variability of the average misclassification rate. Now, in terms of the simulated data, this is how we proceeded. First, we have the predictors. So the predictors actually, we have 10 of them, and the first 8 actually were simulated from a standard normal random variable. And then the other 2, actually, we term them as categorical variables. And for the coefficient estimates, we simulated them from a uniform distribution from -2 to 2 for those numeric predictors. So for the linear predictor, which is given by this long expression, you can see we have our predictors first in linear form, and then we have some non-linear form of them, and then some form of interactions of them. So for the response variable, we use the logistic function or the sigmoid function, which is given by this expression, okay, this expression. And so the actual response variable, yi, is Bernoulli, okay, is two-level predictor, response variable. So we have yes and no. So yes with probability pi greater than 0.5, otherwise no. So we ended up with a data frame, which is given by this form. So at this point, I will hand over to my colleague.
Hello, everyone. To be continue with the methods, we need first, before we do the analysis, we need to build the tree, which is we are going to do the classifications tree using the train data set, which is later on when we are going to partition our data, we are going to use the out-of-bag partitioning the data. So here is like using the train data set to partitions and to build the classifications tree. Also in the terminal nodes, here's where we are going to do all the scenario of the localizations using the KNN in the terminal node. So here is the steps where the KNN are going to do. So that's why like we are going, what we are going to see later in the decision tree, we are going to have a different terminal nodes, and we mentioned to them here mathematically by RL, and the interactions in the terminal node, the interactions between them are going to be 0. So which is the observation should be located in one terminal node. Then the out-of-bag here using the Bootstrap was used here as a test set. This is just like as a review how the decision tree looks like. So decision tree starting with the root node here, then starting to partition or to divide it according to or to split according to the predictors variables until you reach the decisions node here. Then you ended up with the leaf node, which is the leaf node are going to be the terminal node here. So the observation, since starting from here, so we are going to locate in the terminal node here, and also here we are going to control how many observation, and we are going to apply the KNN in those leaf nodes here. So at the end of each tree, so we are going to be, the scenario are going to be here, okay? Now for the KNN as a classifications technique, so we are going to use the test point here, identify the region. So we are going to use the decisions tree that we built, and we are going to, starting with the KNN to identify the terminal node using or to locate the observations. Then we are going to apply the KNN or the K neighbors using the train data set. Then to predict the class here, we are going to use the indicators mathematical functions here using the arguments max here to identify within each test data. So we are going to see our predicted response here where it should going to be there. The misclassifications rate as the evaluations technique here, we are going to calculate it using, we are going to see if the predicted variable are matching with the actual value, and we divide it by m, which is m are going to be the number of observations that we are control it in the terminal node here. So the misclassifications rate. So since we are going to bootstrap with the different scenarios, so we are going to calculate the average misclassifications rate as we mentioned in the objective. So bootstrapping here, we divide to get the average of misclassifications rate, we divide it by the how many bootstrap here. Because we have a scenario of 10 times 50 and 100. So we are going, that's why we ended up with the misclassifications rate here, or the average of misclassifications rate. And to calculate or to compute the standard errors here, so we computed by mathematically formula here. That's because we want to calculate the percentile confidence interval, and our alpha here are going to be the The most common one when alpha are going to be 5%, which is like our confidence interval at 95% confidence interval for the average misclassifications rate here. To outline how the decision tree and hyper methods are going to be worked, so we summarize it like on the step 1 through the step 4 here. So this is one of the scenario. Let's assume that we simulate like 1,000 observations. Number of predictors is 10, which is we have like 8 numeric and 2 categorical variable, as we mentioned early, how we are going to simulate the data, and we define each predictor there. So we move to the second step here, which is, here's the step that we want to partitionating the data to the train and to test using the technique out of bag. Okay. Then after that, we are going to use the train data set to build the tree. So after we build the tree, in the tree here, here's where we are going to control the number of observation in each terminal node or in the leaf node here. So we're gonna, what we are going to see in the results, you are going to see like the result of 5, which means like when we have m equal to 5 in the terminal node up to 55. After that, we are going to compute like, this is how we are going to evaluate the decision tree. In this step, we are going to calculate the average misclassifications rate. Why the average? Because like we bootstrapped it. Okay, then we need to apply like the hyper methods here. Where's the hyper methods are going to be applied? We need to go back to the decision tree in the step or in the first step here. So in the terminal node, we are going to localize the leaf nodes here. Also, we are going to vary k. So varying k here from 1 to m. For example, let's take the scenario if we determine the terminal node to be only 5 observations. So that means like the k neighbors here can take any value between 1 to 5. This is like just one scenario or the general idea how the both methods are going to be combined together. Now here in the result, in the figure number 1 here, we are going to, in the x-axis, here's like where we are going to control or where we are going to track the terminal nodes, which is the size m, for example, from 5 to 55. Then here's like the average of the misclassifications rate in case when we bootstrap only 10 times, 50 times, 100 times. Then we are tracking the misclassifications rate for the hypermet technique and the decision tree itself. So as you can see, among all scenarios here or among different values of m and different scenario for the bootstrapping, the hyper methods are outperform the regular decisions tree itself. Okay. Then in this graph, we are going to track or we are going to add the k neighbors, how many or what k should be. Because as you know, like if you are going to do the classifications using the k neighbors only, maybe you are going to face like the overfitting, underfitting, and that can be like affected by the how or the number of k that you should do. So that's why like we put in our considerations here if we are going to control k as well. So that's why like in the x-axis here, we put different scenario of k. For example, if the terminal node or m equal to 5, so k can be equal from 1 to 5. If the terminal node from 1 to 15, k can take 1 up to 15. Because like as when we defined k can be from 1 to m. And also, again, we are going to, in the y, here we are going to use the average misclassifications rate and different m and how many times we bootstrap, 10, 50, and 100. So comparing the hyper technique and the decision tree, It's so obvious here, like among all different scenarios, the hyper technique was outperforming, which is perform well than the decision tree itself. And I would just like to remind that our data is complex because when we simulated nonlinear. And that's like one of the objectives that we should use the hyper technique, especially when your data are complex and your data nonlinear. And that's like true here. So the conclusions here, the predictive performance of the hyper methods was superior relative like on the comparing to the decision tree itself, as what we have seen like in the plot 1 and the second plot here, among like across the different values of M, different values of K. So the misclassifications rate or the average of the misclassifications rate was like outperform comparing to the decision tree. The hyper decisions method among the consistency like outperform the decisions method, particularly when the local variation is high or the class boundaries were nonlinear. Okay. In conclusions, this result indicates like the potentials of the integrations like of the KNN and decision tree in specifying the superior classification predictive model. Then here for the reference, if you have any questions, so please feel free to email to us, or if you have any comments, any suggestions, also use our emails. Feel free to use our emails and feel free to contact either me or Dr. Thompson. Thank you for having us today, and see you later.
Yeah, thank you.